Hi everyone, and welcome to a new video about noise analysis. In this example number 1, we will discuss the instrumentation amplifier and we will work out the noise analysis for a circuit. And again, we will look at our calculations step by step and verify these in SPICE simulations. So we have the following circuit given. What we have is a Wheatstone Bridge here with 4 resistors, which will actually function as a source that will be connected to the instrumentation amplifier given here by this symbol. It's sort of an operational amplifier, but in this case it is an instrumentation amplifier. And we have 4 resistors again for the Wheatstone Bridge, and we have 1 resistor for the gain to adjust actually the gain of the instrumentation amplifier. Now for this example we have the instrumentation amplifier INA 333. So that is what we have. The 4 resistors of the Wheatstone Bridge are all 5 kilo ohms, and our gain setting resistance is 100.1 ohms. Okay. The calculations are, the required values are the input referred RMS noise voltage, also the output referred RMS noise voltage. So we would like to know what is the output noise in RMS value, and also what is the input noise of this in RMS values. Okay, we also see that there's an input AC voltage here that is necessary. It will be discussed later on in the simulation part to do the actual noise simulations. So let's look at our solutions. Before we move on, of course, let's also look at the instrumentation amplifier specifications in more detail, because we will need those parameter specifications to do the calculations. Now if you look at the datasheet of this instrumentation amplifier, you will see several parameters, and these are what we need actually for our calculations. Instrumentation amplifier on its own is actually composed of 2 stages. So it has an input stage and also the output stage. The input referred noise voltage spectral density of the input stage is given here, which is 50 nanovolts per root hertz, given by this symbol. It also has an input referred noise current density, again for the input stage, so that is also here given by this symbol. It has a value of 100 femtoamps per root hertz. Now it is also an output referred noise voltage density of the output stage, and that is given by this symbol, which has a value of 200 nanovolts per root hertz. And again, it's similar to the actual op-amp noise specification. We have 1 over F noise voltage density and also the 1 over F noise current density specified at some frequency, but for this instrumentation amplifier those are 0. So this is a little bit different than actually the op-amp noise specifications. So in more detail we will see that the cutoff frequency also, or what is called the signal bandwidth of the instrumentation amplifier, will be determined actually by the gain of the instrumentation amplifier, and this gain is set by this resistor RG. Now this can be determined also from the datasheet of this instrumentation amplifier. Now let's look at it in more detail. This is a part of the datasheet of this instrumentation amplifier. What you see is actually the gain. Let's say for what gain is 1, you have actually a bandwidth like this, so you can actually estimate what your bandwidth is. And you can also see for the gain is 10, for 100 and for 1000. In the plot on the right side you can see on the left axis, which is the vertical axis, you can read off the noise voltage spectral density, and on the right vertical axis you can read the noise current spectral density. And you can see that the input referred noise is actually calculated by the input noise squared plus the output noise divided by the gain squared, and then of course square root of that summation. Now this will be clarified in great detail later on. Now what you see here is of course the gain and also the associated cutoff frequencies, or the bandwidth, or the signal bandwidth. But this can be also seen in a table from the datasheet in more detail. For gain is 1, for example, you have a bandwidth of 150 kilohertz. So we can read it also from here, but this is of course much easier. And in this case, for 10 or 100 or 1000, you can also see the associated bandwidth. So you can see actually when the gain is increasing, the bandwidth will decrease, or the gain bandwidth product will stay constant. Now, what you also see actually, there are some values here. This value, which is called the input noise, is actually here 50 nanovolts per root hertz. That's actually this part. So this is actually for the input noise. So the input noise voltage spectral density for the input stage. So you can also look at this part of the graph. So that is actually 100 femtoamps per root hertz, which is the input noise current density of the input stage. So that's actually also very important. And the final one, this line, which is then given in pink here, and that is the output noise voltage spectral density of the output stage. So that is then 200 nanovolts per root hertz. So those are all available from this plot, but is of course summarized here for future reference. Okay, that's what we have now from our datasheet. So let's move on and look at the circuit performance. Of course, we need to look at the gain, and also from there to the bandwidth or the frequency specifications. So we have the closed loop signal gain, and from the datasheet actually what we get is just gain. So the formula for this instrumentation amplifier, the gain, is given by this expression. So datasheet will give you the formula for this instrumentation amplifier. So G of this instrumentation amplifier, short INA, is 1 plus the 10 to the power 5, so 100,000, over RG, which is actually this resistor. So what we have, of course, here is 100.1. So if I now just substitute the values, I will get 1000 for my instrumentation amplifier gain. That is also the signal gain directly. So we'll just equate that to this instrumentation amplifier gain. The closed loop noise gain, which is of course what we want to use in our noise calculations, is also the same for the signal gain. So the signal gain will be also the noise gain, and that will be also 1000 for this instrumentation amplifier. The bandwidth, of course, we have the closed loop signal bandwidth and also the closed loop noise bandwidth. Now, we of course look at this again, the table we have already discussed. And you can see for a gain of 1000 here, 10 to the power 3, you will have a bandwidth from our datasheet, which is typical. So the minimum and the maximum is not given, so the typical value is 350 hertz. So that's actually what we have. That is directly also our signal bandwidth. Now, the closed loop noise bandwidth is then calculated. Of course, we need to make a conversion from the signal bandwidth to the noise bandwidth. For that, we need to assume, or we need to make a very good estimate what kind of system this is. So in this case, we can assume it is a first order system or first order circuit. And for that, we need a Brickwell conversion factor, if it is a first order system, of pi over 2. That's actually this K sub n. Then the closed loop noise bandwidth will be then given by this K sub n, which is then the conversion factor, times the signal bandwidth, which is then 350 hertz. You just substitute the values, you will get 550 hertz. That's actually what we have as our noise bandwidth. Now, if I now move on and look at the total noise, of course we have the input referred RMS noise voltage and also the output referred RMS noise voltage, but those together of course has some relation with each other. That is given by this expression, which has the noise gain, and we know that already. The noise gain of this one is 1000, of course calculated using this value and also the formula given in the datasheet of this instrumentation amplifier. Okay, the input referred RMS noise voltage is, in this case, is also composed of 3 parts. It has the input referred RMS noise voltage due to the instrumentation input stage, that's this value. It has the input referred RMS noise voltage due to that instrumentation amplifier output stage value, and it has also the contribution by the resistors in this Wheatstone Bridge, which is the thermal noise voltage. So we will also calculate each of them and then add them up using the root sum of squares. But let's look at the model, which is a simplified model of this instrumentation amplifier. What you have is the input stage and the output stage. These are the two sources, two noise sources, noise current source and noise voltage source of the input stage. And we can see that the input stage has a gain of G. That's actually what we have as 1000. And this is actually the source, noise voltage source, actually of the output stage. And that has on its own a gain of 1, which is actually most of the time the case. So this is actually what we have. So we actually three parameters here. And this is of course connected to the source, so that will be of course has also some effect in terms of terminal noise. So that will give us actually this expression. So this, of course, in RMS values can be converted to the spectral densities by looking, of course, per root hertz. Then we have the input referred noise voltage spectral density is then the square of that input referred noise voltage due to that input stage, and also that reflected this one to the input stage by divided by the gain, and again squared, and also the contribution by the resistors due to that 4 resistors here. So that's all reflected on the input. But we know we want to have the RMS value. For that we need to multiply this by the square root of the noise bandwidth. If you do that, you will get this expression, and you will have actually, instead of small letters, capital letters, and actually you can use this directly. So it is actually what you prefer. You can use this one or this one directly. Most of the time we will use this one and then use noise bandwidth to calculate this one directly, which is then the input referred RMS noise voltage. But let's look at it in more detail in the next step. So let's first look at the Wheatstone Bridge. We have actually the 3 or 4 resistors here. Of course, in terms of noise, so looking from the point of view of a noise analysis, the DC sources will be, of course, shorted. So all DC sources will be disabled. It means actually in this case we have voltage sources, VEE and VCC will be a short. That creates actually a ground here and also a ground there. That creates actually the following: the R1 and R3, so R1, which is connected actually to this node 2, and R3, all actually are going from this node to ground, and these are actually connected then in parallel. So you make actually parallel combination of R1 and R3. That is also the same for R2, because that goes also to ground from this node 3. And you see that also R4 goes to ground. So you have the R2 and R4 will be also a parallel combination. Now, we have of course 4 resistors all equal to 5 kilo ohms. So we have also the same parallel combination. So we can denote them as just one symbol. I just denote them as R. Then we have the following expression just for the parallel combination. R1 in parallel with R3, which is of course equal to the R2 in parallel with R4. That will give you 2500 ohms, because it is 5 kilo ohms for each, and if you have exact same resistors equal to each other in parallel to resistors, that will be of course just the half of that value. So we have this, we will use that later on. Now what we need is of course the input referred noise voltage spectral density due to this 2 resistors combination, to R1 and R2. That counts also for this R2 and R4. And I need actually the input noise voltage spectral density due to this parallel combination, and also the noise current source, which is then by this instrumentation amplifier, which is then the value of this instrumentation amplifier, and we will use that from the datasheet. That is also for this one, so we have also the contribution by the input noise current source from the instrumentation amplifier, which is now flowing through this parallel combination of R2 and R4. So we have actually 4 parts which will make up that input referred noise voltage spectral density. So then the input referred noise voltage spectral density of this Wheatstone Bridge will be then actually this. So it has these 4 parts. Okay, let's again look at the parameters. This is actually just from the datasheet again repetition what we need. So where we have of course this, and this is the 4kTr. What we know here is then the K is the Boltzmann's constant. We already discussed this also in the previous videos in great detail. The T is the absolute temperature, which is then in this case 300 kelvins. This is the Boltzmann's constant, and the R is actually what you have in this case, so which is then a parallel combination of R1 and R3, which is 2500. Now, if you do the math, you will get 6.43 nanovolts per root hertz. The similar form for the next one, which is of course exact same, so we get exact same value. The next one is this, because this is the input noise voltage spectral density due to this parallel combination, and also the input noise current source by this instrumentation amplifier. You will look at this, which is of course that input noise current source. You multiply that by the parallel combination of these two resistors, and you do that also for the next time for the parallel combination of the R2 and R4. That is shown here, 0.25 nanovolts per root hertz. In a similar case, you will have exactly the same 0.25 nanovolts per root hertz. Now I will combine these four values in here, and I will have actually this result, which will give me 9.1 nanovolts per root hertz. That's actually what we have as the contribution, just due to those resistors from the Wheatstone Bridge, and also of course the input noise current source from the instrumentation amplifier. Now let's then look at the input noise voltage density what we have at the moment. Now we have already given this expression. I now have this, and this is what I have from my datasheet, and this is also what I have from my datasheet, and this is actually what you have from your instrumentation amplifier using this gain setting resistor. So the parameters again, this is 15 nanovolts per root hertz, which is this one. This is what we have used in the calculation of the input noise voltage spectral density for the Wheatstone Bridge. This is what we have here, which will be placed here. And this is the value here that we have calculated, which is 9.1 nanovolts per root hertz. And this noise gain, which is then 1000. So if I now add them up here in the expression, I will get 50.8 nanovolts per root hertz. That's what we have now for our input noise voltage spectral density. Okay, what is an output noise voltage spectral density, which is really easy calculation, because if you know the input voltage noise voltage spectral density, you just multiply that by the noise gain, you have the output noise voltage spectral density. So it is then times 1000, you will get 50.8 microvolts per root hertz. That is really simple. Okay, the next one is of course we would like to go to the RMS value. So the input RMS noise voltage is then calculated using the noise gain, and that is also for the output RMS noise voltage. So the noise gain, I mean the noise bandwidth. Noise bandwidth was 550 hertz. So I will do then the following expression and then calculate actually this times the square root of our noise bandwidth, and if I now substitute the required value, I will get 1.19 microvolts RMS. In a similar form, I will do that for the output RMS noise voltage. Again, I have this from the output noise voltage spectral density times the square root of our noise bandwidth. I will get 1.19 millivolts RMS. So I have actually the required values for my calculations for this example. Now we need to of course check the values also in the simulation. But before we move on, let's also look at the signal to noise ratio, which is a very important parameter. What is a signal to noise ratio, or for short SNR, is a measure that compares the desired signal level to the noise level. In a more precise way, it is defined as the ratio of the signal power actually to the noise power, and it is often expressed in decibels. So if you have a ratio which is higher than 1 or greater than 0 dB, if you express it in decibels, that means you have more signal to noise. But if you have of course the value which is then the ratio which is between 0 and 1, means actually less than 0 dB, which is then negative, that means you have more noise than signal. What you want of course is more signal than noise, so you want to actually increase your SNR, so you want to maximize this. Now for this circuit, the SNR at the output for a specific frequency can be calculated using this formula. And again, that will give you again directly in the values as units of decibels. Now we have calculated this 1.19 millivolts RMS for our output noise voltage, and if I now calculate it and just substitute the value in here, you will get 58.5 dBs, and we will check this also in our simulation. So let's look at the simulation. First one, the output noise voltage spectral density. That's this plot. What you see is actually following labels. I will discuss this shortly. From the simulation, you can see the output noise voltage spectral density is 50.85 microvolts per root hertz. And you can see the cut frequency here is, because I just selected what the value of this is at, let's say, very low frequencies, and how far I need to go in frequency such that this ratio is 1 over square root of 2, which is then the definition of the bandwidth. So that is then the cutoff frequency, and that is then at 387 hertz. So that's actually our cutoff frequency from this plot. So these two labels from the plot are summarized here in this label. We have calculated, it was the output referred noise voltage spectral density was 50.82 microvolts RMS, so very close to what we have here, but the bandwidth is a little bit lower in our calculation, and the simulation will give you a larger value. Why is this the case? Now, from the datasheet, we have actually just selected the typical value of the bandwidth associated with our gain of 1000. That's just a typical value, because the actual model might have, of course, some slight differences or slight changes, which is not matching the data exactly. So this difference is not really that a problem. If you, of course, have a huge difference, for example, this goes all the way to 800 hertz, that's of course what you need to consider in great detail, but this is perfectly fine in the manageable error we can have for our calculations, because we are just working with typical values and not minimum, maximum, etc. Okay, let's also look at the total RMS output noise voltage. This is the plot, and there are several labels here, and I will discuss why I placed those labels here. What we had calculated was the total RMS output noise voltage was 1.19 millivolts RMS, and it was actually a little bit accurate, this value 1.192 millivolts RMS. But we have, if I go and integrate all the way to the end, I have 1.26 millivolt approximately RMS at 1 gigahertz, so actually that's actually the final value. And if I now compare this with what I have calculated, I see approximately 5.5% error, which is not that much again. So for noise calculations, you don't have to be alarmed if you have an error of 5 or 10%, because that's pretty perfectly fine. If you do it in a practical sense, you will see the error that is much larger. That is very normal for noise calculations and also noise simulations, and in particular for noise measurements. But what we most of the time use is the integration bandwidth for our noise analysis and to compare that actually with our calculations, because the bandwidth of our circuit will limit, of course, our noise integration. So in theory, we will need to, of course, integrate all the way to infinite frequencies, but we know that we have a signal bandwidth of 350 hertz. And if I go as a rule of thumb, which is most of the time used by engineers, 1 decade higher in frequency than my cutoff frequency or my signal bandwidth, which is then 3.5 kilohertz, and look at that frequency, what my output noise voltage is, that's actually shown here, then it will give me 1.21 or 1.206 millivolts RMS at 3.5 kilohertz. And this value is much closer to that value, and it's approximately 1.5 or maybe 2% error. Again, very small if you just look at the integration bandwidth. So in summary, if it is simulated and you look only at the integration bandwidth, you will have 1.206 millivolts RMS, which is very close to what we have calculated. So this is a nice result from the calculation, also from the simulations. The signal to noise ratio, SNR, this is the plot what we have, and we have calculated that using this formula. this was the output referred RMS noise voltage, and this was the calculated value, 58.5 dBs, and I see in the simulation it is 58.0 dBs, so this is also very close to each other. Why is this lower? Because the actual output noise voltage in RMS was a little bit larger. That also decreases the SNR of the simulation, so that's not really a surprise. So that's actually now for our signal to noise ratio in the simulation. Now we will also jump now to the actual simulator and see how to generate these plots, and why do I need also this source, AC source here. So I will also clarify this in great detail there. So let's jump to the simulation in SPICE. Now we are now in our SPICE simulator. You can see this is our instrumentation amplifier. This is the gain setting resistor, and these are the 4 resistors of our Wheatstone Bridge and the power supplies to power up the instrumentation amplifier. Now this is the output node, and this actually is just needed to able to do the noise analysis. So if I remove this source, AC source, and try to do the analysis and the noise analysis, I will get this error message. So I will need an input, so I need to add an input. Okay, if I now place it back, just again my dummy source, we don't do anything about it, so you don't have to care what kind of source it is. So if I just click on it, it doesn't matter if it is a unit step or a sine or whatever, just an AC source, place it there, and then just run your noise analysis for the output. Okay, noise analysis, and you can see now it will run. I will make these points a little bit smaller, that will increase the simulation speed 1000. So if I now run this, and I will then generate actually the signal noise ratio, output noise voltage, and also the RMS values for the output noise voltage. Okay, I can see that the plots are generated. You can see actually a green and a dark red line. Dark red line, actually this one, I can see, you can also see that in the label, so I will make it larger. That's actually just for the input, so you can ignore that. That's just, of course, 0 all the way. So I will just ignore that. So this just, we just ignore this, and also for this case, and also for this case, and also for the signal noise ratio. Okay, this is the output noise voltage spectral density. You can see it is 50.85 microvolts RMS, I mean microvolts per root hertz. It will then approach 0 due to that frequency limiting of this instrumentation amplifier. So you can see that by looking at the cursor. Now, if I go to the input noise voltage spectral density at the input, you can see it is perfectly fine 0. Why? Because this is just the source. It is actually grounded in both places, so it is just 0. If I of course also look at the total noise voltage in RMS, the output, again my cursor, it starts at 0 and then increases and actually approaches a value which is settling at 1.26 millivolts RMS. And we have of course discussed this. We had approximately 1.19, so approximately 1.2 millivolts RMS, so that was an error of approximately 5.5%, which is just perfectly fine for noise calculations and comparison in the simulation and calculations. Of course, if you use the rule of thumb to go to the integration bandwidth, which is 10 times the bandwidth of your system, which is then 350 times 10, which is then 3.5 kilohertz, then you will get this value, which is then much closer to 1.19, so 1.19 millivolts RMS. So that's actually what we have discussed. Now you can also see the signal noise ratio, and if I now, for example, make this plot a little bit better, don't go all the way to -100, for example, to 0, or maybe even to 50, lower limit. You can see actually it starts very high for low frequencies, and then goes down, and then approaches actually a steady value of, let's say, 58 dBs. That's what we have in our case. And this is how to generate the plot in Spice Simulator. So we have discussed the calculations step by step for this instrumentation amplifier circuit with a source of a bridge circuit of 4 resistors, so Wheatstone Bridge. And we have seen the signal to noise ratio calculations, we have seen the input and the output noise voltage calculation, and we have verified this using these simulations. I hope this was very clear for you in terms of also in different amplifier or different circuit topology, in this case the instrumentation amplifier. This is our first example about the instrumentation amplifiers. We will do more example. If you have any questions, comments, please let me know. I will try and answer them as soon as possible. Thanks again and see you next time, and take care.